And we're back. Welcome back from the weekend. Today, we will continue on with our discussion of random variables. But before we begin, we'll go over a few administrative bits. The reading due today, the 24th, which is Tuesday, is Barron Chapter 3, Sections 3.1 to 3.2, pages 40 through 46. Do a little bit every day. It'll put confidence, put a swagger in your step. Make sure you read every day. It's not a lot of pages, but it will still require you about at least an hour a day for this class. All right. So when we last left off, we talked about random variables as representing the outcome of a measurement over some observation. And we used the 3-coin flip example. And in this, we constructed a table of the different values the random variable big X can take on and the associated probability. And so we said this catalog of probabilities is called its distribution because it depicts how all of these probability masses, or weights, if you will, are spread out or scattered about over the different values that the random variable X can take on. And so we looked at it in a graphical form, and we said when we take this graph and look at the envelope of this graph, it gives us a tool, an important tool, that will allow us to compare the behavior of two systems with one another. So a kind of calculus, if you will, that we can use to reason about stochastic systems. So let's look at vectors. Now, this is a picture of Leipzig, Germany, and you can see there's a lot of color. There are a lot of things going on. And when you describe things in the real world, you don't just describe them one way. For example, apples have a shape, they're round, and they have a certain color ranging from greenish to yellowish to red. And there are all sorts of ways collectively that you can use to describe things around you. And so we've only been talking about a single random variable. You can absolutely have multiple random variables corresponding to the same thing that you're talking about. So to describe things in the real world, you measure them in different ways. For example, the photographs that I showed on the previous slide, you could talk about the color, right? Red, greens, blues, all sorts of colors. The texture, which is the pattern of variation of color over space. The shape of things, which is the geometric arrangement of edges. You could talk about temperature, for example, if you have a temperature sensor, etc. And so each one of these quantities that you can measure over a piece of data, your observation, are measurements of outcomes. And therefore, their values are stochastic or uncertain. And so this idea of using random variables just isn't a neat mathematical tool. They also tie stochasticity to the real world, to sensed phenomena. And so let's define two random variables, big X and big Y, and let's assume X and Y are pairs of measurements. So if you construct a vector, a two-vector specifically, consisting of X in the first position, or the values that big X can take on, and random variable Y, the second position, or values that random variable Y can take on, this is a so-called random vector. Now, of course, I'm depicting a two-vector, but you can have more than just two measurements. You can have 10 measurements, you can have 100 measurements to describe some phenomenon or some item. And so this represents what's called a vector of random variables. Oops, let me set my pen here. Forgot to do that. Blue seems to be a good color. So this represents a vector of random variables. And as a vector of random variables, because each position represents a random variable, now instead, if we were to talk about the distribution, we would talk about the distribution, or the when can I see you again, those probabilities associated with all of the possible values that can be assigned to both of these random variables that correspond to your vector. So for example, you could have a value of X is equal to 1 and Y is equal to 2.3. You could have a value of X is equal to 7 and Y is equal to 4.1, for example. And so when we talk about the distribution for this random vector, we're now talking about the distribution or the probabilities, the probability math associated with all possible values or instantiations that you can have for the positions, each position representing each measurement or outcome assigned to the random variable. So an instantiation of a so-called vector. All right. And so the distribution of a random vector also has another name. And this other name, it's a synonym, distribution of random vector. It's called a joint distribution. And it's called a joint distribution because the values, in this case, the value taken on by x and the value taken on by y, appear jointly, or they appear together. And so you can also, when you look at this joint distribution, you can also talk about the distribution of the individual values x, or the individual value that y can take on. These distributions have a name. If x and y originated jointly together, they're so-called marginal distributions. And so let's take a look, and we'll consider what happens when you have these vectors of random variables above and beyond having just a single random variable whose distribution we talked about in the previous module. And so if you talk about now the probability associated with an instantiation of your vector, it's still a probability mass function, or PMF, but now you notice here that our mass function is defined on the vector, the ordered pair xy in this case. And so probability of value, remember that same standard where lowercase is a value and uppercase is the random variable. So the probability that value x is taken on by random variable big X and value little y is taken on by random variable big Y, that probability of these values x and y taken on by random vector big X comma big Y is equal to xy. So here when we say P of xy, that's the probability that random variable x, random variable y take on respectively values x and y. Now if we were to list this in set event-like notation, we'd say that's the probability that random variable x takes on value little x, that's true, and at the same time, random variable y takes on value little y. And we say and at the same time because as a joint distribution, what we're saying is the probability or the likelihood or the when can I see you again for these two things to occur together at the same time. Now this occurring together is what makes it a joint distribution. Okay, so if we were to look at all of the possible values that this random vector consisting of random variable big X and random variable big Y will take on, all of these values you can think of, and we've heard this before, mutually exclusive and collectively exhaustive. So what does this mean? That means that the intersection, mutually exclusive, that doesn't change when we have a vector, between any two individual events in instantiation are going to be independent from one another, pairwise. They do not overlap in the Venn diagram, and they're collectively exhaustive, right? Meaning that the union of all of these possibilities represents the entire sample space omega. And so what this means is when you have these properties, mutually exclusive and collectively exhaustive, it's the same as we talked about in the single random variable case and in the event version of things, that the joint distribution completely describes the aboutness or the dataness of the behavior of the random vector. And so this property I will demonstrate with a simplified example. And in this example, let's assume I have an event consisting of two components. I have a coin, a fair coin, and this fair coin, the outcome I'm going to measure with random variable C. And I'm just going to measure the presence of what I see. It's either going to be a heads or a tails. And then I also roll a fair die. And this fair die, its outcome is going to be measured by random variable D. And that's going to be a 1, 2, 3, 4, 5, or 6 as usual. So now I take the die and the coin together and I throw them on the table, in essence, rolling the die and flipping the coin at the same time. Now, I don't have to throw them physically at the same time. I could roll one and flip another, and I'm looking for the joint occurrence of various outcomes from each one of them together. So I'm going to represent this random vector, C comma D, and C is going to be the outcome, one of them, H or T, heads or tails, and D is going to have an outcome, 1, 2, 3, 4, 5, or 6. Now, we're going to list in a table along the rows, we're going to list the outcomes of the die, and you'll notice we have 6 positions corresponding to the 1 outcome, 2 outcome, 3, 4, 5, or 6 outcome. And then along the columns, we're going to have the coin flip outcome. We notice we have 2 columns, one marked heads, the other marked tails. Now, in each cell, if I have a position here, the first row, the first column, that's going to represent an outcome consisting of a heads for the coin, because I'm in that first column, and a 1 for the die. So that's my first outcome. So if I look at every single cell, and there are 12 of them in this table, that each cell corresponds to each of the 12 different outcomes I can have associated with this random vector consisting of the measurement of the outcome of the coin in C random variable and the outcome of the die roll in the D random variable. And so C and D can take on values. C can take on heads or tails, and D can take on 1 through 6. And the joint occurrence of this is going to be represented by each cell in this table, depending on which row and which column you index. Now, in each cell, we have a number written, and that number is 1/12 in every case. And if you're curious how I got 1/12, well, it's 1/2 for the outcome of the coin flip times 1/6 for the outcome of the die roll. That's equal to 1/12. And you'll notice here I have 1/12 in every single cell because no one outcome of this random vector is preferred over another. And so when I write this out, this is the so-called joint distribution associated with random vector C comma D, all the outcomes, the probabilities, the when can I see you again, in table format for this random vector involving the outcome of the coin flip and the die roll jointly, our joint distribution. Okay, so now if I take this joint distribution, I could also express the following probabilities. The probability that the coin flip will be heads or tails, or the die roll will be 1, 2, 3, 4, 5, or 6. Now, let's think about the coin flip. One of the things we think about if we want to compute this one-way probability instead of this two-way probability, C comma D, we can actually calculate this one-way probability of C, the coin flip outcome, given this joint probability. And when we do that, that procedure we follow, we call marginalization. And we're going to demonstrate how we do that marginalization. And so essentially what we need to think about is how many different ways for this joint distribution our random variable C can take on a value, say heads, if we wanted to calculate, for example, probability of a heads. Well, we have the heads column here, and now we look at all the different ways that we can have for this vector, this 2 vector, to have an H, a heads, for the value taken on by random variable C for the coin flip. And so when we look at this, remember that when we talk about this event, it's a union consisting of all of the possible ways this D, the die, can take on values given a fixed value of H that the random variable C takes on. And we notice if random variable C takes on a heads, well, what can D take on? It can take on a 1, a 2, a 3, a 4, or a 5, or a 6. So what do? We add each of those elements for that column in the heads to calculate that probability that C took on the value of heads. And so we do the same thing for heads. We can also do the same thing for tails. And so here we see for that column heads, we sum C equals heads and D equals 1, with C equals heads, D equals 2, C equals heads, D equals 3, 4, 5, and 6, and so forth. So we're adding 112 plus 112 plus 112, adding it a total of 6 many times. There's 6 of them. And if we add them together, that's 6 of these 112s, which is 612, which is equal to our 1/2. So we do the same thing with probability that your coin flip is equal to tails. Again, we sum. Now, when you sum, we look at this table, and you can think of each column as a margin, like the margin on a piece of paper. And therefore, this procedure of calculating the so-called singleton or the single or one-way probability in terms of one random variable, it's achieved by summing, and that procedure is therefore called marginalization. Marginalization. And so in order to compute the one-way probability from a multiple-way probability is by this marginalization procedure. Now, we only did it with a two-way probability to get a one-way, but you can also do that with a three-way to get a one-way, or a four-way to get a one-way. And so here you sum down the margins. You can also do that across the margins, which I'll explain in the next slide. And so here, for marginalization, we're saying the probability, and you notice here the subscript is big X, because that's the random variable we're concerned with. The probability that big X will take on a value X, it's the probability the random variable X assumes value little x. That's nothing more than you take the joint probability in terms of xy. Here's P of xy, taking on each value pair xy, each instantiation. And then you sum for all of the different substitutions little y that your random variable big Y can take on. So in that particular case, we're going to have probability of heads for the coin flip, and for little y, we're going to sum for the value of y equals 1, y equals 2, y equals 3, 4, 5, and 6. And so in this notation, this summation, this little y is going to be substituted with 1, 2, 3, 4, 5, 6, and you're going to do the probability of 1, probability of h, comma 2, 3, 4, 5, 6, and you're going to sum those terms together, i.e. marginalization. Likewise, we can marginalize with respect to x instead of y. In this first case, we marginalize with respect to y. So when you marginalize, that means which one are you going to remove? Or removing the y, right, by the coin flip, the die roll, I mean, by summing out over the different die roll values in order to get the coin flip. And in this case, you're summing out with respect to the y. And so here you can sum out with respect to the x. In our case, that would be the coin flip. And we write the probability of y, if we have two random variables, x, y, is the probability that y takes on value little y, which is just the sum, substituting each of the versions of x, that would be heads and tails. All right. So this marginalization, we can marginalize with respect to our die roll to get the probability that the coin flip will be either heads or tails. Likewise, we can marginalize in the other direction. We can marginalize out the coin flip to talk about the probability of a particular die roll equaling 1, 2, 3, 4, 5, or 6, etc. And so in that case, when we marginalize, for example, the probability that your die roll is equal to a 1, well, we take die roll equal to 1, and we say how many different ways can that die roll be 1? We can have a 1 where the coin flip is a heads, and that particular cell would be that instantiation corresponding to heads, comma, 1, or this second cell, that other way, that would correspond to instantiation tails, comma, 1. So we sum them together. And so that's 1/12 plus 1/12. That's equal to 2/12, which is equal to 1/6. And we write that result here. And so we do that for probability of die roll is 1, die roll is 2, 3, 4, 5, 6. So instead, now we're marginalizing with respect to the coin flip. That's the variable that we're getting rid of when we try to calculate the one-way probability for each one of the values that die roll D can take on. So again, we sum along the margin. In the first case, we sum along the vertical margin. In this case, we're summing along the horizontal margins. And you notice here for each die roll, we're getting 1/6 in each case for probability of D equals 1, 2, 3, 4, 5, or 6. Okay. So we compute the so-called marginal distribution by summing along the margins of the joint distribution. This procedure is called marginalization, or we're marginalizing. And this works for arbitrary dimensions. So you can have a 2-vector, a 3-vector, a 4-vector, and the only difference is you're just going to have a lot more summing to do. All right. So let's look at this other definition. We've mentioned this term independence, and we talked about what independence means in terms of conditional. And when we talked about independence for the conditional, we said the probability if A is independent of variable B, that means the probability of A given B is just equal to probability of A. We said knowing something about B doesn't change at all the probability of A. That's one definition of independence. Another definition says that if two random variables, X and Y, are independent, if you're computing the joint probability, that joint probability is just the product of the one-way probabilities, P of X times P of Y, or the so-called product of the marginal probabilities. And so that's another definition of independence. Independence means that the joint distribution is calculated as the product of the marginals. And in fact, in the Venn diagram, we said before, if you have some sample space omega and two events we're calling X and Y, or random variables that measure events and we're calling X and Y, the independent means in the Venn diagram, independence means that they do not overlap. And so if you want the probability of these occurring together, that's just the product of the two outcomes, of the marginal outcomes of the individual probabilities of the marginals. And so independence means, in this case, that random variable X takes on value X, little x, and random variable Y takes on value little y, that these events take on values independently of one another. They occur, but one doesn't require the presence of another. They occur independently. They're just taking on our values independently from one another. Okay, so with that, we'll end here. It's a short lecture so that I can begin a new topic on Thursday. As usual, please make sure you're keeping up on the reading. And next time, we'll talk about some of these calculations that will help us describe quantitatively various aspects of the shape of your distribution. We will look at expectation and variance, and we'll try some experiments in that lab. So with that, as usual, please stay healthy and stay safe, and I will see you Thursday.